In this video, I would like to talk about resonance forms in organic chemistry. Resonance forms are used extensively in describing organic structures, especially when you have an organic structure in which the electrons, especially the pi electrons, are delocalized over a number of atoms. And so we use resonance forms to describe that delocalization of electrons. So some compound structures are then not adequately represented by a single Lewis structure. We need to use multiple Lewis structures in some cases to accurately describe the situation for bonding in an organic compound. So when you have two or more valence bond structures that are possible, the molecule will usually show characteristics of both these structures or all of these structures, and these are called resonance forms. It's important to realize that resonance forms differ only in the placement of electrons, not the movement of atoms. It's not a chemical reaction, but it's just a different way of depicting a structure by the movement of electrons. And these are typically going to involve pi electrons or non-bonding electrons, not sigma electrons. Usually the sigma electrons are left in place, but the other kinds of electrons can be moved about on the molecule. And the actual structure, there's only one structure, even though we draw it in different ways. The actual structure should be viewed as a weighted average of all of the resonance forms, and we call this a resonance hybrid. And to illustrate this, I'm going to again return to nitrous oxide. You can see nitrous oxide here on the left, and it's got a Lewis structure showing a triple bond between the two nitrogens. Previously, we determined that that was actually an excellent depiction of nitrous oxide because the octet rule was obeyed and it placed the negative charge, -1 here, you can see for a formal charge, on the more electronegative element. There's another resonance forms that we could draw, which is shown here in the middle. And in this case, the negative charge is shown on the nitrogen. Now, nitrogen is less electronegative than oxygen, so we thought this one on the left was a better structure. But it nevertheless shows that the negative charge can be shared between the oxygen on one end and the nitrogen on the other end. Now, the way we illustrate that is you can see with these arrows where the electrons are moving. We're taking this pi bond between the two nitrogens and moving it onto the electrons onto the nitrogen. So now it has two lone pairs. And we're also taking a non-bonding pair from the oxygen and moving it to form a double bond with the oxygen. So we're just moving electrons about, and we're depicting that single molecule, which only has one structure, but we're depicting it in two ways with two different Lewis structures. The third Lewis structure that we considered previously showed a -2 on one of the nitrogens, and we decided that was too much charge separation to be an important contributor. So in this case, we have two resonance contributors, and one's a major contributor. This is probably the most accurate way of drawing it. But there's also a minor contributor, which shows a negative charge also on the nitrogen over here. Sometimes you can depict the average of all of these resonance forms, in this case two, but you can see down here I've tried to depict that where instead of a full triple bond here, you have a double bond plus a partial bond. And then instead of a full double bond, it's not a single or a double, it's in between that, then you have a single bond plus a partial bond here. So it's sort of like a bond and a half here. The other thing that's important here is this shows that the negative charge is distributed between the nitrogen on the left and the oxygen on the right. So we have this partial negative here and partial negative over here. And then, of course, you see with these resonance forms up here, the +1 formal charge is always on the middle nitrogen, so we have a partial positive charge on that middle nitrogen. So these delta minus and delta plus indicate partial charges on the atoms, which we have indicated previously. So let's take a look at some other examples of resonance forms of molecules and ions. This first one is called nitromethane. Of course, it's an organic molecule with a methyl group in here, and we have a nitro group. Notice that the Lewis structure is shown here, and the Lewis structure shows a formal -1 charge on one of the oxygens and a formal positive charge on one of the nitrogens. But you can also move these non-bonding pair of electrons to form a double bond between the nitrogen and the oxygen, and then move the pi electrons that help form this double bond to the oxygen, move those pi electrons out onto that oxygen. So that shows that, in fact, that the negative charge that's associated with the oxygens is actually shared between the two oxygens. Actually, these are equally shared. The oxygen equally shares that negative charge. And if you look at a combined representation using the dotted lines to show partial bonds, you can see that each oxygen on average has a formal negative 1/2 charge. So you have a negative 1/2 here and negative 1/2 here for a total of -1 on the oxygens, a +1 on the nitrogen. That makes this overall a 0 charge for nitromethane, but it shows that the negative charge is concentrated on the two oxygens equally. So these are equal contributors. Now another molecule that is illustrated here is formaldehyde. And formaldehyde is an aldehyde in terms of its functionality. It has a carbon double bond oxygen. And it turns out that this carbon double bond oxygen is a very polar bond, with the oxygen being a much more electronegative than the carbon. But part of that polarity is due to the fact that these pi electrons can be attracted to the oxygen. And you can illustrate this with a resonance form of the aldehyde. And so then you can move these pi electrons out onto this oxygen to show 3 non-bonding pairs on the oxygen with a formal -1 charge on the oxygen and a formal positive charge on the carbon. Now, one of the things you'll notice here is that in the structure on the left, where there's no charge separation, you'll see that all octets are there, and that this satisfies the octet rule, and there's no charge separation. So this is considered to be the major way and major contributor to this overall structure. But this one is important in the sense that it shows that the oxygen is actually adopting a partial negative charge, even though it's not a full -1. In this structure it is, but overall it's a partial negative charge on the oxygen and a partial positive charge on the carbon. And also notice that there's no octet on the carbon, so that it argues against that, but nevertheless it shows that there's this charge separation. And perhaps the best way to indicate this is to simply draw the covalent molecule like we did at the beginning over here, but indicate that the oxygen has a partial negative charge on it and the carbon has a partial positive charge on it, with a molecular dipole in the direction indicated here. So we have 2 resonance forms, a major and a minor contributor to that formaldehyde structure. The other thing that I want to point out here, which I did not mention, was that we use double arrows to indicate resonance forms. Just like we did on the previous one, we used a double arrow here, but then we're also using a double arrow here. So this is not a chemical reaction. This double arrow like this, with a single line with an arrow on each end, is used for indicating resonance forms, which means that all you're doing is moving electrons. So we're depicting a single molecule or ion in a more than one way, with more than one Lewis structure. So let's take a look at one more example of resonance forms. In this case, I'm talking about the resonance forms of what is called the allylic cation. This is actually an intermediate that we're going to see in a lot of chemical reactions. And it's a cation. That means that there's a positive charge on a carbon here. And you can see the Lewis structure of this allylic cation over here on the left. There's 3 carbons. All of these carbons are actually sp2 hybridized in this case. So this first one and this second and the third are all sp2 hybridized. And you can see this over on the right, where you have trigonoplanar geometry associated with each carbon. But this cation, the structure on the left, is a little bit misleading by itself, because it shows that the positive charge is sitting on one of the carbons, in this case carbon 3, but in fact it turns out that through movement of pi electrons in this system, the positive charge is actually distributed between one carbon and the third carbon. And so you see that we can draw another resonance forms. And what we're doing here is we're taking these pi electrons and moving them over here to form a double bond here, which in turn places the positive charge on the left carbon here, carbon number 1. So the question is, what's going on here? Well, these pi electrons are actually spread out over all 3 carbons. So we can actually show the double bond here, or we can show the double bond here, which in turn means that the positive charge is shared between carbons 1 and 3. Now, from an orbital picture, you can see what's going on here. These all being sp2 hybridized, each individual carbon would have a p orbital associated with it, and then when you overlap those with each other, then you form what is called an extended pi system. So the 2 pi electrons that are in this system can actually move through this electron cloud here, both below and above the carbon framework here. So what this tells us is that, in fact, there's a partial positive charge on each carbon on the end. So carbon number 1 would have a partial positive charge, and carbon number 3 would have a partial positive charge on it. And so in other words, what we have here is then an average of these 2 resonance forms, and that would be the best depiction of that allylic cation. Now it's important to realize that this double arrow, again, is not a chemical reaction. And if you look at something like this is illustrated in your textbook, it shows that somehow this hydrogen moved from over there to over here. So you had 3 hydrogens on a methyl, and now the methyl group is over here. Well, that actually would be a chemical reaction if that took place. So these would not be resonance forms here. So it's important to note that only you're moving electrons and you're not displacing any atoms when you're looking at resonance forms.